Good morning. This morning I'm going to give, this is Saturday morning by the way, in New York City. I'm going to give an overview of the density of states. That's just off the top of my head with no notes. The full analysis is coming up, it takes about an hour. This one will probably take maybe 15 or 20 minutes. I won't put in all the details. I will derive the density of states. Just the long part is solving the Schrödinger equation for a particle in a box requires a little bit of detail because we're using the separation of variables method. But I can give you an overview and see where it's coming from. Now, what's the density of states? The density of states is the number of solutions to the Schrödinger equation, right? Per joule of energy, yeah, per unit volume. Now, let's define the density of states mathematically. First, rho of E is 1 over V dN by dE, where d by d number per unit volume, which is the number density of states. Now, what are the units? Let's look. Number of states per unit volume is just a number over joules per meter cubed. Actually, that'll do us for now. Well, I can put it in. So the SI units of the density of states is seconds squared per kilogram per cubic meter. Now, what good is density of states? It gets us straight into solid state theory, or the study of the interior of a white dwarf star where matter is compressed, or a neutron star, many things. Not only solid state theory. It's the beginning of our study of solid states anyway. All begins with the definition of density from middle school. Density is mass per unit volume. For example, for water, the density of water is 1 gram per cubic centimeter. This notation is very misleading, that's why I was struggling with it. That means 1 cubic centimeter of water weighs 1 gram. Okay? So therefore then 10 cubic centimeters of water would weigh 10 grams. The density of aluminium is 2.6 grams per cubic centimeter. Iron about 7 grams per cubic centimeter. The density of lead is 11.2 grams per cubic centimeter. That means 1 cubic centimeter of lead weighs 11.2 grams. It could be 0.3 grams. Mercury, I know for sure. The density of mercury is 13.6 grams per cubic centimeter. So therefore then, what can we say? Mass is rho V. We know the density and we know the volume, we can find the mass. Now that's mass density. There could be energy density, yeah? Right, slightly different. Not kilograms, we get joules instead. There could be density of other things, but what happens if the density varies, let's say in a sphere, varies with radius? We integrate. Okay? So this notion of a density is very useful throughout all of physics. Example. The Schrödinger equation, as its solution, gives us the probability density of finding an electron in a certain region, and the square of that probability density gives the actual probability of finding the electron somewhere. Let's clear the board. That's an introductory idea. So what do we do now? Okay, to find the density of states, we construct a model of a piece of metal. Now the electrons are confined within the metal in a kind of an electron sea. So we construct a metal and we put it into the shape of a cube of sides of length L. Why not make it sides A, B, and C? Well, it doesn't matter. The cube can have any shape. This region here can have any shape. It can have any volume. The density of states is independent of shape and volume. It could be a sphere. It could be some kind of triangular object or a random thing. But that would make it difficult to carry out the calculations. Now, a lot of the times you see the density calculated that have different sides, like length 1, length 2, length 3, and length 4, whatever it is for the cube. You don't need that because we're going to keep the volume of the cube L cubed. Yes? Now, what's going to happen? Well, the electrons are confined. They cannot escape this chunk of metal. They stay within the electron sea there. Unless somebody throws a high energy photon at it. That's the photoelectric effect, you know about that. But that's not happening here. So the electrons are confined due to a potential outside here stopping them from leaving, right? So the particles are confined within this region. So we solve the Schrödinger equation such that the following is true. The potential is 0 inside the box and infinite outside the box. And that's what we get. In the x direction. Okay, in the whole direction, now inside the box, what can we say? V is 0. So there's no term like that, okay? So that in the x direction, the solution is we get this kind of an equation. Did I get that right? Plus or simply k squared equals 2me over h cross squared. Now what else do we require? We require boundary conditions. This is the solution in the x direction. We can break up the solution separately in the x, y, and z directions, and then later show by separation of variables, which I'm skipping till the long analysis, that the solution is the product of all three. But let's say in the x direction, The solution to this equation is a sine kx plus b cos kx. Now, we require the solution to be 0 on the boundary at x equals 0 and x equals L. Now what obeys that? The sine function obeys that. That's what sine looks like. Cosine does not look like that. It begins as cos of 0 is 1. So we throw away this part. B is 0. Okay, so that's our solution in the x direction. Let's clear the board now and clear our heads at the same time. Well, that's what we got. And don't forget what kx is. Better carry this thing around. That's what our k was. Now, we need to find out what the a is. Overall space, the electron must be somewhere. So the wave function, psi of x, is normalized to 1. This is mod psi squared. Right? So we get the integral over sine squared is 1/2 times 1 minus cosine 2kx, which is cosine is 0 between those limits, and this just gives me 1/2 x between 0 and L. Which gives me a equals root 2 over L. When I solve for that, and now we know what the a squared is. Now we have the solution in the x direction. Let's get that written up. Get your heads around that. We also require the solution to be 0 when x equals L. So this is satisfied if we make n an integer, any number of pi's, right? Every time you have an integer of pi, the function is 0 for n equals 1, 2, and 3. Now this is only in the x direction. The solution is, what's the word? The same in every direction. Doesn't matter what way you orient the box. So we can say that in general, separation of variables, the solution is going to be the product of similar solutions, similar functions, one for each direction, the x, y, and z, and a cubed is going to be root 2 over L cubed. Okay, so this is the solution of a particle in a box. Let's look at the x direction only first. The derivative of twice gives me in the x direction. If I take the second derivative of this function, it pulls out an n over x, an n over L, and then a second derivative gives me a minus sign because I'm taking the derivative of cosine and another one of these factors. So now we have two spaces, n space and k space. Okay, so far so good? All right. Let's continue now, and we'll extract this and put it up at the top because we don't need a cluttered up board. The product of the three different functions is going to generate something more like this. Okay, so we're going to get the x function, the y solution, and the z solution, giving me kx squared plus ky squared plus kz squared, which I'm going to call k squared. It's a scalar. So that the absolute value of kx squared plus ky squared plus kz squared is that length. And what is it the length of? It's the radius of a sphere. So let's look at that sphere now. It's a sphere in n space or k space, either one. We can choose in either one. We'll work in k space for this. Let me get a drink of an orange juice. Okay, let's continue. Okay, so I like to keep the board uncluttered now. This is what we need. So what we do is we look at that sphere. This point on the sphere we'll call the Fermi level, the Fermi energy, or Fermi momentum is the extreme value of it. The Fermi energy is the energy of the most energetic electrons at the tip of the sphere. Now typically the number n, the number of points in this space, is going to be about Avogadro's number, 10 to the power of 23. So let's look at the points. Let's look at all the possible values for these k. These n's are integers. as you can see, they're all positive. None of them are negative. So we restrict our study to the positive octant. So we don't consider points outside of the positive octant. So it's going to be, if we want to find out how many points in this space, we want to know how many points like that, less than the Fermi energy, less than the Fermi momentum, anyway, less than inside the radius of what? Of the positive octant. Just this, right? So we want to find out the density of states. We'll consider all the positive points inside that octant. Now to do that, we'll have to consider the following. Okay, this number of states is a separate question. The density of states is slightly different. We're going to find the number of points in a shell between k and dk. Well, we know that it's going to be the area of the shell 4 pi k squared dk. But let me show you why that's the case. If we take the number of points inside k, and subtract that from the number inside k plus dk, we get the following. It's the number between k plus dk and this sphere and the slightly bigger sphere. And we have to subtract that. Okay, so that's what we get when we cube this object here. Let's see what happens. This cancels. This is very small, order dk squared. This is very small, order dk cubed. So we're left with this. Well, we're not quite there yet, because to get the n, we have to actually divide by something. I was almost forgetting something. Okay? So let's do that. We'll say it's proportional to that. There's a proportionality constant in here because I have to get rid of that. we have to deal with this C1 here. I was almost forgetting it. Now we consider the volume of a single cell in K space. It's the difference between any two neighboring cells. So we just subtract the difference, subtract this from this one. This is a step ahead of from this one, and we get pi over L. We call this L0. And that's the width of one cell, okay? So therefore then, for one cell has a side of length L0, the volume of a single cell is going to be L cubed over pi cubed over L cubed. That's what our C1 is. It's actually the reciprocal of it. Okay. So now that we can write down what our dn is. It's the volume of our shell divided by the volume of a single cell. Now don't forget what L cubed is. L is the length of a side of a box. So L cubed is the volume of the whole box, the space, the whole space in X space, as opposed to this little dl, wherever I put it, I took it off. So this here has a pi cubed down squares, and the L is upstairs, V0. Okay. So we'll cancel one of the pi cubes. No, this is not V0, this is V space. Okay, now remember this is the volume of a whole sphere, but we only need the volume of an octant. Not only that, so we have to divide by 8. Not only that, if these are electrons, we can have electrons, 2 electrons in each state, okay? Spin up and spin down. So we'll double that to account for the fact that the electrons have spin. And that's what I get, okay? 8 over 8 cancels. So I get k squared over pi squared for this n, and let's erase everything on the board. We'll leave the top piece. we call this dn of k. So now let's work this out. Now we could use the to get from dn by n of k to n of e, we could use the chain rule, but I'm not going to do it that way. I'm just going to take differentials. Now remember that k squared is 2me over h cross squared. V stays the same. And k is this. So if I take a differential of this object here, I get the following. This v is the volume of all the space. This brings out 2m over h cross squared to the power of a half. Sorry. Now, taking the differential of e to the power of a half, I get 1 over 2 e to the power of minus a half dE. Okay, so that's what I've got for dn. So now I'll divide by dE and v. This and this go over to this side. Well, it's going to be 2me over h cross squared pi, sorry, yeah. H cross squared pi squared times over half e. E to the power of a half. So let's go back up here. See what we've got. This thing. This is rho of E. Now I'm missing something. Okay, 2me over h cross squared. Okay, I've got 2m. I forgot those parts. They go in too. Okay, so now I'll bring all this guy up here. The 2's cancel, and I get root 2m to the power of 3 over 2. M to the power of 1, m to the power of a half is m to the power of 3 over 2. And e to the power of a half into e to the power of 1 gives me e to the power of plus a half. What else have I got? Pi squared times pi is pi cubed. Sorry, h cubed. Pi squared. Anything else? That's it. Now we came to this at a long road, so we'll just highlight it because we put it into a box because it's a nice result. Aren't you going to say, bravo, I didn't use any notes, right? So we came by this through a long route. There's a longer presentation, or maybe I'll make a presentation in 3 parts, each one, let's say 20 minutes, so that I'm not rushing through it like this, because my YouTube only allows me to put in a certain amount of time. Anyway, thanks for listening. I'll come back with a more careful, long, detailed analysis, although there was nothing wrong with that. It was fully correct. All right.